Hello, and welcome to a lecture on sensitivity and dynamic range. I'm Steve Ellingson. Here's an overview of this lecture. First, I'll talk about some sensitivity concepts. These concepts include the minimum discernible signal, abbreviated MDS, and also the concept of the noise floor. Then I'll talk about dynamic range. And there's two kinds of dynamic range that we'll address in this lecture. One is blocking dynamic range, and the other is spurious-free dynamic range. So first, minimum discernible signal, or MDS. This is sometimes written minimum detectable signal, which means essentially the same thing. These terms are used more or less interchangeably. The definition is as follows. It's the signal power applied to the input, which results in a specified signal-to-noise ratio at the output. And this is assuming perfect impedance matching and a bandwidth which is at least as large as the specified input signal. So first thing you should note about this definition is that there are a lot of things that have to be specified. One, we'll have to specify what SNR we intend to use as part of the definition. In other words, is an SNR of 1 okay? Is an SNR of 10 required to be considered detectable or discernible? So we're going to have to say what the SNR is. Also, we're going to have to say what the bandwidth is, because it says here the bandwidth is at least as large as a specified input signal. So that's so we get all of the input signal, but then if the bandwidth is larger than that of the input signal, then we're dragging in additional noise, and that's going to change the detectability. So the SNR and the bandwidth have to be specified, or MDS really doesn't make sense as a specification. Commonly specified signal-noise ratios for MDS include 1, which by the way is 0 dB, 2, which is about 3 dB, sometimes 3 dB exactly, sometimes 6 dB, sometimes 10 dB, and this is very application dependent. I would say the most common specification is probably just SNR equals 1. Now, you could legitimately question whether a signal is truly detectable if the signal-noise ratio is only 1, but nevertheless, this will be our convention because it's probably the most commonly used assumption, and it leads to some nice equations. The concept of MDS is useful because it does not depend on an antenna or environmental noise consideration, so it can be measured on the bench in the laboratory. See, if we're interested in sensitivity in a system, we have to account for the external noise, and we have to account for all the things that the antenna can pick up. But if we're designing receivers, we would like a specification for sensitivity that is something we can measure on the bench. And MDS is something that fits the bill there. So here's an example just to show you how it works. In this example, a signal generator is applied to the input of a two-port cascade, and a power meter is attached to the output of a cascade. So here's the scenario: signal generator, there's a two-port, and then there's a power meter. And it's found that an RF tone at -127 dBm at the input results in a reading of +5 dBm at the output. And if the tone is turned off, then we end up with +2 dBm. So presumably that +2 dBm is associated with internal noise. So what's the MDS in this scenario? And also we're told to assume that the signal generator contributes negligible noise. So here's the solution. When the tone is turned off, the power meter is indicating the output referred internal noise of the cascade, as I just pointed out. So we can call that quantity N. When the tone is turned on, the power meter reading is reading N, the internal noise of the two-port, plus the output referred signal power. And the ratio of those two readings is the ratio between these two, which is 3 dB, and that's about 2. So what we know is that S plus N over N is about 2. Now note that S plus N over N is equal to S to N plus 1, which is the same thing as SNR plus 1. So we find here that the SNR is 1. And that was the defining SNR for MDS relationship. So in this particular case, it turns out that the MDS is equal to the applied power, -127 dBm. So you may realize here that the MDS and the noise figure of the two-port must be related. The output referred internal noise power of the cascade we can write as follows. N is Boltzmann's constant times the input referred equivalent noise temperature times the bandwidth times the gain. Now just keep track of units here. This is watts per hertz, and this is hertz. So this whole thing has units of watts. And this is input referred, so when we multiply by G, we're getting the output referred power. The output referred signal power, when the input power is equal to the MDS, is simply the gain times the MDS, right? The MDS is input referred, so to get the output referred signal power in that condition, we just multiply by G. So under these conditions, S is MDS times gain, N is K TEQ times B times G, and that is equal to 1 because of the way we define MDS. So solving this equation, I find that the MDS is equal to Boltzmann's constant times the internal equivalent input referred noise temperature times bandwidth. And if I want this in terms of noise figure, I know how to do that because I know how to go from equivalent noise temperature to noise figure. So this is the expression I get. I can relate the noise figure, or in this case noise factor, to MDS through this equation. One final note here is that obviously since we're dealing with a noise figure, we have to say what the reference temperature is as always. Remember, noise factor, noise figure means nothing until we say what T0 is. And there's a couple ways to interpret T0. So this gives rise to the following consideration. When we do MDS calculations, are we interpreting T0 simply as some arbitrary temperature that defines noise figure? Or are we interpreting T0 as the actual input noise? See, either interpretation can work, but we have to be clear on which one we're using. MDS is K times T sys times B. And remember, the system temperature is the overall equivalent noise temperature of the system, including any input noise. So we can rewrite this as Boltzmann's constant times T in times the input referred equivalent noise temperature, where T in is the equivalent noise temperature applied to the 2-port, times B. Now we can expand this out a little bit further. If we assume that T in is equal to T0, in other words, if we define noise factor such that T0 is actually the input noise and not some arbitrarily set number, then we can write this expression simply by replacing T in with T0, and we can expand this out. So we get that MDS is the sum of K T0 B plus K TEQ B. And I know that I can replace TEQ with the expression for noise factor like so. And so I really see I have three terms here. I have a K T0 B, I have a K T0 F B, but I also have a K T0 B again. So this cancels out with this. And what I'm left with is that MDS is K T0 F B. And again, this is under the assumption that we made right here that Tn equals T0 and not that T0 equals some arbitrary temperature like 293 K. So we refer to this as the non-zero input noise interpretation of the MDS. Now the reason I point this out is because there is a very famous expression which appears in essentially all RF system engineering books that says that the MDS in decibel units, typically in dBm, decibels relative to a milliwatt, is minus 174 dBm per hertz, plus the noise figure in decibels, plus the bandwidth in decibel units. And that's simply this expression here. K T0 is this thing if we now say that T0 is 290 K. So in effect here what we're saying is that T in is 290 K, and then we get this expression, right? And then here's F, and then here's B. So this is just the log form of the previous expression. There's really no difference between these other than the fact that I've made now the assertion that T0 and subsequently T in is 290 K. So this is a non-zero input noise calculation for MDS, and it's a different result than we get if we assume that there is zero input noise to the 2-port. So let me show you a calculation which demonstrates the difference here. The bandwidth and noise figure of a receiver are 30 kilohertz, so that's going to be B, and 5 dB, that's going to be F, respectively. So the first question here is, what is the MDS assuming the zero input noise definition, the first one we came up with? And then what is the MDS assuming the Tn equals T0 definition? So here's the solution. Again, B equals 30 kilohertz, F equals 5 dB, and we have from the zero input noise definition that the MDS is minus 125.9 dBm. If we use instead the Tn equals T0 definition, then we have minus 124.2 dBm. Now what we see here is that we have two different values of MDS, and the reason they're different is because in one case we assume zero input noise, in the other case we're assuming the input noise is equal to the reference temperature. And that's really the only difference. So the receiver in this case is no less sensitive. The receiver is equally sensitive. It's simply that we've defined the input noise condition differently. So this underscores the importance of understanding the definition that's at work when you do these calculations. And when you report these calculations, you need to say very carefully under what conditions you are making the calculation. And I'll note here that in the second case, we can also use the famous equation, the log equation, and of course you should get the same number as you calculated here, minus 124.2 dBm. Now, in that first example we did, where we had the signal generator, and the 2-port, and the power meter, let's assume that the bandwidth was 30 kilohertz. And then we can ask, what is the noise figure? Well, assuming the noise figure was defined with respect to T0 equals 290K, then the zero input noise definition, if we solve that equation, gives us that the noise factor is MDS plus KT0B over KT0B. We computed the MDS in the previous example. KT0B, again assuming T0 is 290K, is minus 129.2 dBm. So making the substitution into this equation, we get a noise figure of 4.2 dB. So now we have a taste for how practical calculations can be done with MDS and how we can compute things like noise figure if we have an experiment which suits that calculation. Note you cannot use the T0 equals Tn method here because its assumption about the actual in situ noise is incorrect. Remember in that previous example we said that the signal generator contributes no noise. If it contributes no noise, then Tn is 0. It is not T0. So you have to be very careful about applying the definitions in a way that's appropriate to the scenario that you're actually evaluating. Now, the concept of noise floor. So to understand the concept of noise floor, you can look at a spectrum, and this is a spectrum that would be the output of a receiver or some stage of a receiver, and this is frequency, and this is power spectral density. Now remember, power spectral density has units of watts per hertz. It's how much power we have per unit bandwidth. So what we typically see is we see a pass band. The pass band consists of some central region where it's approximately flat, and then stop bands, and here's the two stop bands. So what noise floor is this talking about the central region where the spectrum is approximately flat. And the definition is that's the power spectral density of the noise in that central region. So if we take some amount of bandwidth at delta B and we measure the power in delta B, then it's that power in that bandwidth divided by that bandwidth, assuming again the spectrum is flat. So noise floor is really the power spectral density of the noise in the central region where the pass band is flat. Now, you should note that this is often reported as a power, not as a power spectral density. And the reason is because when you make this observation on a spectrum analyzers will report power. But when they report power, they are assuming that you are aware of what the resolution bandwidth, what delta B is. So for example, you might set a quantity, it's labeled different things on different analyzers, but RBW, for example, might be 1 kilohertz. And then you see that this level here might be reported as a minus 120 dBm. But what it's actually telling you is that that's minus 120 dBm in 1 kilohertz, which is minus 150 dBm per hertz. And that's actually the power spectral density. So don't be confused by that fact. Here's an example, returning again to this previous example that we just talked about. Let's say the gain is 50 dB. What is the output referred noise floor in terms of power spectral density? Then let's say we terminate the input into a very cold matched load and observe the output using an ideal noiseless spectrum analyzer with a resolution bandwidth set to 1 kilohertz. And then what does the spectrum analyzer indicate as a noise floor? That's the whole problem. So the solution goes like this. The output referred noise floor is just K times the input referred equivalent noise temperature times the gain of that 2-port. And again, TEQ can be calculated using this expression for the noise factor. And from that, we get minus 121.8 dBm per hertz. And that's the answer to A. That is the output referred noise floor in terms of the power spectral density. A very simple calculation. Now, if we terminate the input into a very cold matched load, that says what we're doing is we're disconnecting the signal generator and we're applying some thing which has very, very low noise. So what we're really saying is that the applied external noise is negligible compared to the internal noise. It can't be zero exactly, but it's going to be tiny and something we can ignore relative to the internal noise generated by the 2-port. So in that case, the spectrum analyzer is measuring only internal noise. That's the significance of that statement. Since the noise floor power spectral density is minus 121.8 dBm per hertz, we just calculated that, and since the resolution bandwidth is 1 kilohertz, the spectrum analyzer shows a trace which is greater by 30 dB. That's 10 log 10 of 1,000. That is minus 91.8 dBm. See, we started off with this, the power spectral density, minus 121.8 dBm in 1 hertz. So if we have 1,000 hertz, that goes up by a factor of 1,000, which is 30 dB. So we get minus 91.8 dBm. Now, dynamic range. Dynamic range is broadly defined, and I emphasize broadly, as the ratio of the powers of the strongest signal and the weakest signal that can be simultaneously accommodated by something like a receiver without unacceptable distortion or loss of sensitivity. And the way to understand that is that just imagine what you have with one signal. If that signal is sufficiently large, we have a linearity problem. If that signal is too small, we have a sensitivity problem. So there must be a range of signal values for which we can operate this receiver, and for which neither linearity or sensitivity will be a problem, that we can accommodate both issues. Now, strong signals challenge the linearity of a system, which in turn make it more difficult to receive weaker signals that are simultaneously present. In other words, if we have a sufficiently strong signal, it creates things like intermodulation products and gain compression and things like that, which degrade our ability to receive weaker signals that we could have easily received in the absence of that stronger signal. So this is what dynamic range measures, is the ability to do both, accommodate strong signals while still being sensitive to weak signals. We would like some number or some definition that tells us our ability to do that. So for practical use, we need specific definitions, and I should say now there are many, many ways to define dynamic range. I'm going to talk about two, and even these two can be defined in many ways. But the two most important ones, I would say, are blocking dynamic range and two-tone spurious-free dynamic range. So first, blocking dynamic range. The definition of blocking dynamic range is the ratio of the 1 dB compression point to the minimum discernible signal. In other words, you measure this, and then you measure this, and it's the ratio of the two. Now, as I just pointed out, there are several variants of this definition, depending on how precisely you define MDS, because remember, there's not just one definition of MDS, and whether you consider the MDS to be the value in the presence or in the absence of the blocking signal, right? In other words, one way to measure this would be to first measure the 1 dB compression point, and then drop the signal level, and then measure the MDS. So that's measuring blocking dynamic range in the absence of the blocking signal. Alternatively, I could apply a strong signal, get to the 1 dB compression point, and then, while that signal is still there, apply a weaker signal and try to measure the MDS. And those are going to give me two different results. So I have to be very clear about how I'm going to do this blocking dynamic range measurement. Other versions of this metric exist using different sensitivity criteria, that is, alternatives to MDS. In land mobile radio, in certain other applications, instead of MDS, we measure audio signal to noise ratio. Maybe we apply an FM signal, for example, and then demodulate it and see what the audio signal noise ratio is. SINAD is signal to interference plus noise and distortion. So that's another audio metric that we could use. And as in all dynamic range metrics, if accuracy matters, you have to be very, very clear on the test conditions. Already I've shown probably half a dozen ways in which these tests can differ in subtle ways. And I'll point out here that data sheets are notorious for their murkiness on this kind of issue. So it's very common to pull up a data sheet for some receiver, for example, and it'll say simply blocking dynamic range is this. Well, that doesn't really tell you a whole lot. Maybe if you have 10 receivers from the same company, maybe they used the same blocking dynamic range measurement technique, and then you could compare the receivers. But I would certainly not use that number to compare company X's receiver to company Y's receiver simply because they both said blocking dynamic range. The other metric is two-tone spurious-free dynamic range. And here what we have is the spectrum. There's a noise floor evident here. And I'm applying two tones. So there's my two fundamentals. And we know that if the linearity is limited, we will end up with third-order intermodulation products. And those third-order intermodulation products will end up at equal distances on the outsides of those two fundamentals. And we know that they start off pretty weak and they get stronger and stronger as the applied, that is the fundamental tone power, goes up. So what we do in this measurement is we increase the power of the fundamental tones until the intermodulation products reach the threshold that we have previously defined as being the MDS. So the reason that's a useful dynamic range measurement is because in the absence of this signal, we know that we could detect, or we could usefully use signals at the MDS level. And then this linearity test is telling us at what point the intermodulation products could potentially overwrite or block or obscure signals that we would otherwise be able to receive. So then we say that the difference between that level for the fundamental and the MDS is the spurious-free dynamic range, and specifically the two-tone spurious-free dynamic range. Now I'll note that once again we have this issue: are you measuring two separate measurements and then taking the ratio, or are you doing it all at the same time? So one way I could do this is to first measure the MDS using just a single weak tone, and then I can remove that tone and I could do a measurement where I figure out where the IM3s hit the MDS level. That'll give me a potentially different result than if I first set this scenario and then I apply a new signal up to the point where I meet the MDS. Those could potentially lead to two different results. So you have to be clear on which way you're doing it. One of the reasons we like two-tone spurious-free dynamic range is because there is an elegant relationship between that metric, the input third-order intercept point, and the MDS. And it's illustrated in this diagram. So in this diagram, I have input power and output power. And we know that for linear gain, that relationship should be a straight line as shown here. And we know that we have this concept of third-order intercept point in which the intermodulation products are coming up like this. And eventually they intersect what a result that we'd get for a linear gain device. But remember, this is a mythical point. We never actually get here because the whole thing is experiencing compression, so we do this. Nevertheless, we use this point to quantify the linearity of the receiver or whatever device we're interested in. Now, it turns out that this line has a slope, at least if we do this in log units, of 3 times greater than the linear gain. Right? This has a slope which is equal to the gain, and this has a slope which is 3 times greater. The intermodulation products come up 3 times faster than the linear gain would suggest. And over here, I'm indicating the MDS. The MDS could be anywhere on this curve, but for the purposes of illustration, I'm saying it's here. And that implies a certain level at which the IM3s would be equal to the MDS. So we see right away that this distance here is equal to the two-tone spurious-free dynamic range. Now the reason this whole business becomes useful is because I know that the distance from here to here is simply the distance from here to here divided by 3. How do I know that? Because the slope of that line is 3. So this distance right here is equal to the input IP3 minus the MDS divided by 3. Again, this is in log type units in dBm. Well, see, if I know this distance here is equal to this, and I know what this distance was, then I know what the spurious-free dynamic range is, because it's the difference between the two. So spurious-free dynamic range must be 2/3 of that difference between the input IP3 and the MDS. So this is a very useful expression. Again, it implies a couple things. It implies that you've measured all these things properly, that you have a common definition for what they are, that the third order polynomial response model is applicable, and so on. Nevertheless, this is an often used way to estimate spurious-free dynamic range, or at least to know what the relationships between these three quantities is: the spurious-free dynamic range, third order intercept, and MDS. So here are three quick problems, three quick examples, which show you how we use these kinds of relationships. In the first example, we were told that the input IP3 is plus 10 dBm, and the MDS is minus 110 dBm. Now, what's the spurious-free dynamic range? Well, we just apply the equation. It's 2/3 of plus 10 minus 110, which is 80 dB. So in this case, we'd say the two-tone spurious-free dynamic range is 80 dB. Now, I'll emphasize here that what you get for MDS differs depending on the definition you apply. But this calculation doesn't take that into consideration. It just assumes that we all agree on what MDS is. So in terms of this problem, we will always get the same answer. However, if we have different opinions about what MDS actually should be, then this number would change. In the second problem, we're told to continue, and we have, when we're measuring the spurious-free dynamic range, what is the input power of the applied tone when the IM3 is equal to the MDS? So this is a very common question to ask. We're doing the measurement of spurious-free dynamic range, and we want to know or be able to anticipate what input power for the applied tones corresponds to the case when the IM3, the third order intermodulation products, are equal to the minimum discernible signal. Well, since the power of each intermodulation product is equal to the MDS, as we've indicated here, then the input power of each tone is simply the input third order intercept point minus that distance I showed you on the previous slide, the difference between the IP3 and the MDS divided by 3, and so we find that the input power is minus 30 dBm. Finally, continuing the previous examples, estimate the blocking dynamic range. Well, blocking dynamic range we have defined as being the 1 dB compression point minus the MDS. And if we employ the rule of thumb, the input IP3 minus 1 dB compression point is 9.6 dB. Recall we talked about that in a previous lecture. Then we may estimate the BDR to be plus 10 minus 9.6 minus 110, which gives us minus 110 dB, which is a very common kind of number to see. In fact, all these numbers are pretty commonly encountered numbers for receivers. Now note here, the additional assumption we made was this one, that the difference between the input third order intercept point and the 1 dB compression point is about 9.6 dB. And that is based on the assumption that the device or the receiver is following the memoryless polynomial response model. So to the extent that the device or receiver does not follow the memoryless polynomial response model, this will be an error. So here's a summary of what we've talked about. First, sensitivity metrics. There are many. They include MDS, which can be defined in multiple ways. They include noise floor. Neither of these is bottom line. In other words, neither of these is kind of an absolute metric, because the true sensitivity is modulation specific. In other words, what a user cares about is what they hear or the quality of the data they get, right? And we have not yet considered any of that. This is only about the sensitivity of RF blocks, and we've done this in a way that is independent of the modulation. So the true sensitivity of a system depends on the modulation performance as well as other things. Nevertheless, this is useful as an RF design specification. So it's routine to specify that a receiver should have a certain MDS or a certain noise floor or so on. And then somebody else has presumably done the work to figure out that's going to be good enough when used with a certain kind of modulation to yield a certain bottom line sensitivity. We talked about dynamic range metrics, including blocking dynamic range and two-tone spurious-free dynamic range. And there are many other kinds of dynamic range metrics that we could have talked about, but we'll see even with these two, things can get pretty complicated. And an overarching lesson to learn here is that it is very easy to make mistakes by not fully understanding the definitions. And these definitions get tinkered with all the time, and people frequently do not fully disclose the particular definition they're using. So you can't simply look at a data sheet that says that the spurious-free dynamic range is something and assume that that is a certain definition, such as what I've shown here. You really need to, if it's important to you what that value is, you need to look carefully at how it was calculated. This concludes this lecture on sensitivity and dynamic range.